Thank you. Industry Informatics Department, we have two teams. One is optimization, led by Zdeněk Hanzálek. Another one are embedded systems, led by Michal Sojka. So, quick update about us. Currently, we have 4 senior members, 2 postdocs, 10 PhD students, and more than 10 master students working with us, and Pavla Svítilová, our administrator, helping us a lot with a lot of administration work. We have a new postdoc, Corentin, he's sitting over there, and 2 new PhD students. Jan Čevic, he's sitting at an exam, but Viktor Koladinov is over there. So those are our new promising members of the department. Regarding results, we published or have accepted 14 journal papers. 4 of them are in D1, and 13 conference papers, where 6 of them are ranked as A-star conferences. Pepa Grus finished a very important contract for S3 Microelectronics, and Peter Stejskal got last year Siemens Award for his work. Because we concentrate on cooperation with other teams, because that's like related to the topics we address, we created a new website where we present our projects and skills. So if you type idd.circ.cvut.cz, you can see our new website that may present better what we are doing, and if you are interested in joint cooperation, feel free to contact us. Cooperation, especially inside CIRC, is very important for us, so I'm happy that we managed to publish this year a joint paper with team led by Mikuláš Janota. It's a publication in a very good journal in operations research domain. Another joint paper is with team led by Ondra Mamula, which is in applied energy, and it's a D1 journal where we never published before. Regarding cooperation, Zdeněk Hanzálek leads RoboProx project, which is a very large project really focusing on cooperation. Inside CIRC, there is Mikuláš Janota, Petr Kadera, Robert Babuška, and Libor Přeučil, if I haven't forgot anyone. And this summer, we prepared a large project, Toucher Sigma DC5, with many of you. So it was a summer joint adventure with Professor Mařík, Tomáš Pajdla, and many others, and also the project department. I want to thank for that, specifically Petr Šamánek and Anna Tahovská. It was really extensive work over the entire summer. Last slide. Last year we succeeded twice in the evaluation of the excellent results. One of our paper was ranked as an excellent, and we also succeeded with an application. It's specifically the hybrid power plant, and the score was 2. And now I will pass word to the first speaker, who is Willem Heinz.
Thank you.
The floor is yours.
Okay, so good morning, everybody. My name is Willem Heinz, and I will present a joint work with Peter Willem and Professor Zdeněk Hanzálek with the name Reinforcement Learning for Search Tree Size Minimization in Constraint Programming. So very briefly, let me introduce what constraint programming is. So it's a mathematical declarative programming. We have variables to which we can assign values that are defined by domains, and we have constraints that constrain the variables together. The principle of constraint programming is about searching. In the search phase, we assign values to the variables, and then propagation, which checks if all the constraints hold. It is a NP-complete formalism, so it provides same expressivity as integer linear programming, which might some of you know. And it provides a wide variety of modeling constructs, which helps to provide much faster solutions for certain problems and more natural representations, which can be seen if we check the formulations provided on the slides for the same problem in CP, which is on the left, and ILP, which is on the right. So specifically, we were working with a solver called Optar CP Solver, which is a novel solver with state-of-the-art performance. we were provided a extended academic collaboration, so we had a complete access to the solver insights. And the solver is made out of 3 main components, but we focused only on the failure-directed search, which is a method of the solver how to extensively explore the solution space. So, as I mentioned, it is a systematic exploration of a search space, which guarantees the optimality and uses a search tree structure. So, each tree node is essentially a branching choice, which is an assignment of some set of values to a certain variable. So, if we look at the image on the right-hand side, we can see that in each node there is a decision that splits the domain of variable usually into 2 parts, 2 distinct intervals. The core principle of the algorithm is to try find infeasible sets of choices, so some path in the tree, and if the set of choices is infeasible, then we know that the following subspace contain no feasible solution. So if we again look at the image, and on the leftmost path, we can see that by 2 assignments, x is greater than 4 and y is greater than 3, we will reach a infeasible subspace and we no longer have to explore it, which saves us time. This is guided by a mechanism called choice rating, which represents past successes and failures to obtain the infeasibility by a given choice. And the choices are picked by the rating, so always the choice with best rating is picked unless it's already in the tree. The motivation for this was that when comparing CP and ILP, ILP is usually stronger in the exhaustive search part. So if we look at the right-hand side, CP is generally faster at the start and provides better solutions. But if we want optimal solutions or proofs, ILP is usually faster. So our goal was to reduce the infeasibility set size to provide more optimal choice selection. So if you look at the tree, the ordering of the choices matter in how fast we can explore the whole search tree. And the shallower search tree means, of course, shorter runtime. So the problem actually was how to efficiently and accurately do these rating assignments for the assessments for the choices and how to avoid good choices being found late, which was the problem because FDS greedily always picked the best choice, so we could sometimes never explore or find the one that was better. So this is where the reinforcement learning came into play. So probably most of you know the famous exploration-exploitation dilemma, which is when to pick the best known action that we know of and when to test new underused actions. In this case, we use the multi-arm bandit problem framework. So it is a single state, usually stochastic environment where we are trying to maximize the expected cumulative reward. So if we look at the image at the bottom, we can think of it like multiple slot machines where we have different probability distributions over the rewards, and by pulling the lever, we will get some reward, but we never really know which distribution or which slot machine is the best. So there are different algorithms and ways how to handle the exploration. We considered 4 of them: epsilon greedy, UCB1, Boltzmann exploration, and Thompson sampling. In the paper, we shown that the FDS choice selection is equivalent to this map problem. So actually, the map algorithm goal is the search tree size minimization. However, there is a small issue in this case because map-based exploration can be really costly in the FDS. Because we have a tree structure, if we add bad exploratory choice, we can double the search tree size. So we make 2 small adjustments to the algorithms. First one, we kind of hybridize it in a sense that most of the times we just exploit the best choice, but only occasionally we let some of the map algorithms to decide the choice for us. And the second one was if we decide the choice by the map algorithm, we try to test run it, evaluate its effect, and update the rating. And only if the choice does not open 2 new branches, meaning that at least 1 branch is infeasible, we will use it. Otherwise, we do a rollback, which you can see on the image on the bottom, and we instead of use the exploitatory choice. So we compared 4 different algorithms, multiple levels of hybridization. I showed just 2 in this graph. And we also tested how the choice rollback affects the results. And we found out that cautious explorations is actually the best. So Boltzmann hybrid strategy was performing best with 90% of greedy choices and only 10% of Boltzmann exploration choices with choice rollback. So if we look at the graph, we can see that the algorithms had very different performances, and the Boltzmann exploration also provides the biggest stability, which can be seen from the error bars. So by using this reinforcement learning in the FDS, we actually managed to improve lower bounds for one of the most famous scheduling problems. So in just 900 second time limit, we managed to improve most of the open job shop instances and more than half of the RCPSP instances, while also closing some of them completely, thus proving the optimality. On average, we were 2 times faster than the FDS without reinforcement learning, and we also outperformed the state-of-the-art concurrent solver called IBM CP Optimizer by 3.5 times in job shop and 2 times in RCPSP. We succeeded on the preprint service SSRN, where we were first in February and March of 2025 in the operation discrete category, and we were published in the Q1 journal Computers and Industrial Engineering. That is all from me. Thank you for your attention. And if you have any questions, I'll be happy to answer them.
Thank you. Next speaker is Sojka.
So, good morning. I am going to present recent work that we have done together with Honeywell company, and it's about thermal modeling and optimal allocation of avionics safety critical tasks on heterogeneous MPSoCs. So this work was published last year in a journal of parallel and distributed computing, and it's an extended version of paper which received Best Paper Award on RT-CSA conference some years back. So what is it about? Honeywell, they do a lot of avionics components. Those components need to be powered by some computation. Nowadays, MPSoCs, so-called multiprocessor systems on chips, which are systems which comprise of different kind of CPUs, GPUs, and a lot of peripherals. This is the norms how such systems are built. The specificity of MPSoC is that there are different kind of CPUs. Typically, some are high performance, another one are more energy efficient, so that the designer can find like trade-offs between energy consumption and performance. In avionics, they have lot of constraints, so it's difficult to use those modern technologies there, and basically our work contributed to allowing them to use those kind of technology better. Specifically, we looked at how to improve thermal efficiency, how to run more software. Of course, if you want to run more computations on a system, you have to cool it. Nowadays, normally you can cool it with fans, but it's not possible in the airplanes. And also, if you put a lot of heat sinks into the airplanes, it's too heavy, or it might be too heavy. So the goal was to figure out whether there is something that can be done in software, use some software techniques to reduce the heat production so that the heat sinks can be lighter in the airplanes. We dealt mainly with scheduling. To do this kind of research, we built several test beds. So here you can see one test bed, NXP IMX board with MPSoC CPU here, a lot of sensors, measurements, power sensor, temperature sensor, a lot of automation so that we can run many experiments. Another test bed with similar CPU, with thermal camera, and some airflow cooling so that we can better see the thermal effects with the camera. And we ran a lot of experiments. For example, here you can see a real-time view of one of our experiments. The CPU is running some workload on a different kind of CPU, and with some image processing from the thermal camera, you can see where is heat produced on the chip, and depending on where the workload is running, you can really see that the heat is produced at different parts of the of the chip. So with this tooling, we did some investigation of how the chips actually work, how they are designed internally, and we can basically reconstruct the chip layout. We could identify that the energy efficient cores are located here, high performance cores are located here, GPUs are located here. We can even distinguish between multiple those high performance cores, and we can also distinguish between different parts of the memory hierarchy, like L1 caches, L2 caches, and DRAM controllers, and all these things somehow contribute to the heat production of the chip. So we learned about the chip. Now we have to know about the workload which needs to be executed on the platform. In avionics, it's a bit different from what you are probably used to. They use so-called cyclic executives, where everything runs cyclically in so-called scheduling windows. And the idea is that certain tasks running on different CPU cores should not overlap with tasks in other window, and the idea is to prevent interference between those tasks for safety reason. So if you want to run the workload, the question is how many windows you have, how long these windows will be, and at the same time, which task will be running on which CPUs, which task will be running on energy efficient CPU, which task on performance CPU. To answer these questions, we designed several thermal models which somehow describe the task to be executed. We invented or used some optimization methods found in the literature, and we run many experiments, like days and weeks of experiments, to confirm our results on 3 different hardware platforms, 2 IMX from NXP and one NVIDIA platform. So I talked about thermal models, so to have some idea what a thermal model is in our work, we had like a lot of benchmarks. Each benchmark is described by few numbers which represent different qualities or different aspects of the benchmarks. And here on the right-hand side picture, you can see how those models can predict the temperature of the chip. The black line, if you can see it, it's like the measured temperature. The dots are the predicted temperature. You can see that some models are better, some worse, but they somehow can predict with some precision. So these were thermal models. The second component was optimization methods. So as you will see, the most successful optimization method was based on integer linear programming and the sum-max thermal model, which you have seen in one of the pictures below. Another optimization methods were different kind of black box optimizers or non-informed heuristics and so on. To go into the result, the best method that we have designed was called ILPSM. This is the method which performed the best on all 3 hardware platforms that we have evaluated, and on all sets of benchmarks like CPU-bound benchmarks and mixed, meaning CPU-bound and memory-bound benchmarks. The second best method was this black box optimizer, basically genetic algorithm, again with this sum-max thermal model. And to present a bit more intuitively how our results actually look like, you can see it here in this slide. These are the schedules produced by our algorithms. So let's concentrate on this shortest schedule. This achieved like the highest performance, everything run very quickly. And here on the graph at the right, you can see like the temperature of the platform. If you use some naive algorithm, you can get like high temperature or high temperature. If you have our algorithms, the temperature is a bit, not much, but a bit lower. In this case, the platform runs as fast as possible. You get every CPU cycle from it. It's not very interesting. It's more interesting if you allow the platform to run a bit longer. You have more time, you don't have to run as fast as possible. And in that case, if you just take whatever schedule you had here and just spread it so that it's a bit longer, you get some temperature reduction, of course. But if you not only rescale the schedule, but if you recompute the schedule and reoptimize from the thermal perspective, you get much higher temperature reduction. And this is caused by the fact that the algorithm moves tasks from those performance scores to those energy efficient scores, which are displayed at the bottom here in this graph. So overall, with this technique, we can save like 15% of the, let's say, thermal power and produce less thermal power. So to summarize, we performed many experiments. We identified that our proposed algorithm is the best. The second proposed algorithm, which doesn't need expensive solver, was also pretty good. And you can benefit from, if you have more time, if the platform is not utilized 100%, you can benefit more from our algorithm. Thank you. That's all from my side.
Thank you, Michal. Next speaker is Lukáš Chrpa.
Okay. So I will be talking about the concept we call planning against nature. So it is a joint work with RS Chrpa from Technion from Israel. And so the idea is that usually in classical planning, we just generate planned sequences of actions and that's it. But if we actually would like to use the technology in practice, such as in robotic or human-robot collaboration, so that actually the environment is rarely static. There are some events that can change the environment. And the issue is that, you know, if the environment modifies itself, so it can provide, it can not only disrupt agent plans, but it can also lead to some more dangerous situations. So the idea is that here actually the task of the work is to provide some formal guarantees that the agent safely achieves its goal. Now, sorry. So, to give you some background of anything, anyway, to give you some background about planning, so that we can represent the environment by so-called state variables that are variables with finite number of values. Then we have actions. Each action is defined by its precondition, which means which values of given variables, you know, has to be true in a given state in order to apply the action. And if the action is applied, so that we have effects of action, which says how the values of variables change. In our case, we have actions of the agent, but we also have actions of the nature. So to disambiguate, we call them events, because they just happen without the consent of the agent, right? I mean, syntactically, we can define events in the same way as action, with preconditions and effects, but semantically, they have a different role, because we can assume that the nature can trigger any finite valid sequence of events between agents' actions. So it means that we also kind of pessimistically adjust for time, because in our models, we don't explicitly model time, and sometimes agent actions might be longer than nature events. So here we are kind of safe that if we say that any finite valid sequence of events, so that we can adjust for that. But what does it mean? So it means that basically the nature can do a lot of changes. So basically the exponential number of changes, because we have still the finite state space, but given different sequence of events that might happen, so that it can lead basically to exponential number of possibilities. And in our case, we consider two different kinds of nature. One is fair nature, where we assume what is called strong fairness assumption, which is roughly speaking that if an event can occur, it has non-zero probability to occur. But there is another type of nature, we call it adversarial, where there is no fairness assumption, where the nature actually can do what it wants to disrupt the plan of the agent. So to give an example, if we have adversarial nature, then here on the left-hand side we have a ship that might disrupt the plan of the AUV, which is trying to collect the resource. And since the nature is adversarial, we don't know when the ship will move, right? Therefore, we can't really safely go here and collect the resource. On the other hand, if we know that the ship is moving in a different direction, and if we don't assume in our model that the ship can turn around, then we can safely collect the resource over there. If the nature is fair, however, so that what we can do is that we know that the ship is moving this way, and since we have fairness assumption, that we can assume that the ship will eventually move away, and then we can safely pass and collect the resource. So a little bit more of technical details. So when we talk about robust plans, that this is a sequence actions that the nature can't really invalidate, right? So therefore, even the adversarial nature has no chance to disrupt the plan. And what we are looking at is, when we are generating these plans, is how the nature can modify the environment. And we can see that if some state variables are changed by the nature, so that we can't be sure if the action has these variables in the precondition, that it can be actually executed. Right? So that we have some algorithm in which we pessimistically estimate by what is called delete relaxation, where we just don't, let's say, remove facts that were achieved before. Therefore, it gives us pessimistic assumption what the nature can apply and how the variables can be changed. And therefore, we look for actions that are not only applicable in the given state, but also if each variable is not affected, it has only one value. So that here the illustration is like, what the nature can do in here, right? So that if we assume adversarial nature, so that, it can move ships on all these fields, and we can't be sure where the ship can be in the next step. So the method is sound but not complete. We have some paper in the review with a complete method, but this is still in the review, so maybe next time I will be presenting it. But with a fair nature. So the idea is that here we can somehow assume that the nature will do some events at some point. Here again, so we focus on sequential plans. But here there is also one aspect, which is that we might be waiting for something that the nature will do in future. So if you recall the example that the nature can just move the ship away and we can pass. And here, if we can extend actually the method for robust plan generation, because in fact, robust plan has stronger assumptions, therefore it will also work for fair nature, but it is too restricting. And here we somehow can assume that we can, that the nature can trigger some events for sure, and also that some facts might be safe, because even if the fact is deleted by the nature, there is non-zero or there is guarantee that eventually the nature will achieve it. So as it is illustrated here, that ship will eventually move away. So yeah, just to quickly summarize that we presented a framework which we call Planning Against Nature, which provides some formal guarantees for safety even in dynamic environments. So we still keep the benefit of classical planning. We have sequential plans that are easy to explain, and also in our incomplete methods, the plan generation takes similar amount of computational resources as in classical planning. And here a small advertisement. So we are developing with our students a tool that visualizes and simulates plans against nature. And this has been just presented on the demo track of AAAI conference. Okay, thank you.
Thank you, Lukáš. Are there any questions? Yeah. So I started the blog, so I will also conclude it. This is a joint work of Jan Pikman, me, Claire Hanen from Lipsis at Sorbonne University, and Zdeněk Hanzálek. And the topic covers passive surveillance systems. Unfortunately, the topic is more topical than I like, but let's see. Passive surveillance systems like Věra NG is a system which is produced by a Czech company, and it's a successor of a famous system Tamara. And it's a system that is meant for detecting targets, and those could be air, ground, or naval targets. And the principle of this system is based on multilateration, meaning that if you know position of some points and you know the distances to the target, and if you have sufficient number of those distances with specific accuracy, you can estimate the position of the target. The system uses so-called time difference of arrival. So there are different sensors of the system, and the system detects the difference between the arrival of the electromagnetic signal to the sensors. The best characteristic of the system is that the system can cease without being seen, because unlike radars, the system is not emitting any signal. It has just set of sensors in the landscape and just waiting for the electromagnetic pulse being projected to those sensors. It can be used to track in 2D or 3D, and nowadays it's used as a part of defense networks and for electromagnetic warfare. Michal, can you play the video illustrating the system a bit? So imagine that you have a aircraft or whatever else system, and there are like several sensors nodes of the system. And whenever the electromagnetic pulse emitted by one of the targets hits like all the antennas, then you can reconstruct a 3D position of the system. And of course, the system is able to track like multiple targets at the same time. And in addition, it's able to analyze from the type of the pulse, what is it? What type of jet plane is it? What type of radar, and so on. Thank you. Thanks. The system has typically 4 sensor nodes, and each of them has a receiver or multiple receivers. And there are 2 main tasks of the system. One is a survey, and it's an operation that is meant for detecting new targets, and it's sufficient if the signal is received on a signal sensor node only. So the scenario is illustrated here. So we have 4 sensor nodes, and for the survey it's enough if we do this operation on single sensor node only. Another operation is track, which is used for really tracking position of the targets, and for that we need all 4 sensors at the same time. The connected issue with those operations is that we have receivers, but they cannot observe the entire frequency band all the time, because that's really huge, it's physically impossible, and that would generate so much data. So then it comes opportunity for scheduling to optimize that. So I'll use an example to explain like the core principle of the problem. We have 2 tasks, green one, survey, and the red track, and they are illustrated here. T1 stands for T stands for tracks, S for survey, and there are like different frequency bands. Survey is typically a large frequency band which we survey and search for the new targets. And for each such a band, we have a prescribed rate, meaning how often we observe this frequency band. Targets that are illustrated with red color are typically characterized by shorter frequency bands. We also have some prescribed rate, how often we want to observe them, but the main difference is that a target can be observed on multiple frequency bands. So that's the input. Then we have the receivers that are on different sensor nodes. And for example, here we configured the one sensor node, one receiver, to observe those yellowish frequency bands. So we realize part of this survey operation. For tracks, we need to allocate all 4 sensor nodes. And the task is to, or the problem is to create the so-called tuning plan. Those are like configurations in time for the system, which frequency bands we are supposed to observe, such that we respect the prescribed observation rates. The problem is known in the literature as the resource management for such systems, and it has been studied intensively for radars, but not for passive surveillance systems. So our paper is one of the first in this field, and in our work we have shown that this problem can be translated to the mathematical problem called multiple interval coverage. For this type of problem related to the passive surveillance system, we did a complexity analysis of those problems, and the paper which came from this analysis is currently presented by our colleague Jan Pikman at AAAI conference in Singapore. We also created an algorithm for this problem, an algorithm able to create the tuning plan in real time, and this work is currently under review in computers and operations research. Thanks for your attention.